I'm Tom Ptacek, and we are here today to talk about detecting virtualized rootkits. To my right are my other research team members. This is Nate Lawson over here. Nate Lawson, formerly of Cryptography Research, the author of the unbreakable BD Plus Blu-ray DRM standard, which you should ask him about because it's actually quite cool. And Peter Ferrie, AV researcher from Symantec. The three of us jointly have been spending the last 9 months or so working with research that my former Matasano colleague Dino Daizovi, who I wrangled into sitting next to us for no apparent reason, did last year on the Vitriol hardware virtualized rootkit, which we'll talk more about in a second.
And Tom is from Matasano, a services firm, and they do a lot of work with enterprises clients. And this all sort of came out of a conversation we had last year together after the Vitriol and the other virtualized rootkit discussion about how we go about detecting these. And so here's the results.
So we did actually rehearse this talk, but I feel like the more I rehearse things, the worse I do in actual talks. So the one thing you're not supposed to do in a talk is apologize before the talk about the talk, and here we go. So let's start really quickly just by talking about what we're going to talk about in this particular talk. This will take us just a few seconds. So what we want to do is we want to give everyone in the audience a recap on how hardware virtualized rootkits work. This is the idea that underpins the Blue Pill hardware virtualized rootkit, and Joanna will be somewhere in the audience. You can raise her hand and I can introduce her. Hey. Somewhere in that direction. We applaud, by the way. It's fantastic work. So I want to explain how this stuff works as quickly as we can to get to the meat of how we're doing detection. Then we want to make... Can you hear Nate? Sound check?
Test.
Yeah. Am I fine now or am I not fine? Still not fine? You know what? It's too far away from my Utah while I fix.
Okay, so I'll cover this real quick. We're going to cover how Blue Pill works and how basic VT rootkits work. Vitriol, we're going to explain why nothing is 100% undetectable. There's always something you can observe in a system. We'll talk about our implementation of a test framework and the particular tests we used that allowed us to issue the rootkit challenge. And then finally, we're going to talk about where this is all going to end up in, say, 10 years, where basically you're stuck in a cat and mouse game, and it's exactly like the AV ecosystem we have today.
Let's try again. Any better at all? I assume so. You can raise your hand again if I'm totally inaudible. So, like we said, to start with, we want to talk about how hardware virtualized malware works. In particular, how our hypervisor rootkit, Vitriol, from last year functions, and then what we understand to be the differences between our hypervisor rootkit and Joanna's hypervisor rootkit. So, to start with, we want to put this in context. So, there's been an arms race of stealth malware, of rootkits and of viruses trying to hide themselves from detection code for as long as we can remember. You go back to the early 80s and there's that famous apocryphal story about the compiler backdoor, which when it compiled the login program would inject a backdoor into the login program. And when the compiler compiled itself, it would insert the compiler backdoor into the compiler, which, by the way, is far more clever of an attack than almost anything, maybe save Joanna's work. Far more clever than most of what we see from malware authors today. But this arms race proceeds through, for instance, Dark Avenger and the MTE polymorphic viruses stuff. So we had polymorphic viruses and, after that point, so we entered the epoch of much harder to detect viruses. In the 90s, we had kind of a race through the rings of the operating system, starting with HideSource, the original Solaris rootkit, which simply backdoored the login program, a userland binary, and kind of proceeded through KVM, the interface that userland uses to speak to the kernel. And from there into the kernel itself with things like Josh Damont's amodload, which actually built an entire new module loading interface into the closed source Sonos kernel. So we've seen this notion of kernel malware and kernel rootkits, things that insert backdoors into computers but use the operating system or the capabilities of the environment to hide themselves, going way, way back. And that goes through the late 1990s with the IAT rootkits and the SSDT rootkits and backorifice and
One of the key things here is that we've seen this before. We've seen someone claim the sky is falling, there will be some kind of rootkit that won't ever be able to detect It'll be in the kernel. You won't be able to do anything about it. And people have always found countermeasures, and we expect this is going to continue the same way.
So getting into the actual technical detail right now, one of the things that I want to make clear to you is that the way hypervisor rootkits work, or hyperjackers work, differs from what you're probably thinking of if you're familiar with virtualization, but not familiar with hyperjacking and virtualized malware. So we have this concept of like what VMware does, where you have a guest operating system running completely contained by the virtualization environment. So it's not doing anything that isn't in some way, shape, or form controlled by the hypervisor. So you have the operating system effectively running on top of the hypervisor. And I think that last year when we introduced the notion of hypervisor rootkits, people kind of walked in with a misconception about how these things work, namely that what a hypervisor rootkit is a very slim hypervisor that you would install under the operating system, and that can install itself and uninstall itself on the fly. That's not really true. What we're working with is a concept that's slightly different from virtualization, and we call it hyperjacking. And hyperjacking is the idea of using the virtualization capabilities of your platform, in our case, the Intel VT instructions that allow Intel hardware to be virtualized, to set up a trap handler so you can intercept certain things that the operating system is doing with the hardware. This is different from what real virtualization is doing because you haven't taken over all of the hardware interfaces that the operating system is using to speak to the hardware itself. If you had to do that, you'd have a problem that was as hard as what VMware has to do. VMware is a multi-billion-dollar company with very smart engineers gradually replicating all the device driver stack used by the operating systems that they emulate. Hyperjackers don't do this. They're much smaller than that. Most of the operations that a hypervisor rootkit is dealing with are passing directly from the operating system to the underlying hardware.
So please elide this from your memory, the slide in the middle, because no one actually implements it this way because it would be an untenable solution.
So again, the native operating system is speaking directly to the hardware. Think of the hypervisor rootkit as in some way running alongside the native operating system and simultaneously punching the running operating system in the nuts. That's essentially what hyperjacking does. Now, if any of you guys are familiar with web application penetration testing, and this is a labored analogy, but I'm going to try it anyways. If you've ever tested a web app, right, well, you know that you don't have tools that are customized to every single web application you use. What you have is a web proxy in the middle, right? So most of the complexity in a web application lies in the endpoints when you're testing it. It lies in the browser, and it lies in the web server. And if you want to test that and find vulnerabilities and exploit vulnerabilities in web applications, what you do is you put a component between the browser and the web server that passes almost all of the operations for that web application directly between the browser and the web server. And what the proxy does is it allows you to pick and choose which operations to look at and which operations to modify. And in a web application, modifying means inserting a single quote in a field or something like that, right? Well, it's very much the same thing with the hyperjacker. Like I said before, the hyperjacker isn't getting in between the running operating system and all the different pieces of hardware running there. What it's doing is it's picking and choosing which hardware operations to intercept and to work with. But like in the web browser scenario, most of the complexity in this environment resides in the endpoints. And we're going to use that phenomenon here against virtualized malware. One other thing I want you to keep in mind is because the hyperjacker itself, because the virtualized malware like Vitriol, because that system doesn't implement all this logic, but instead passes it through, it's quite small and quite easy to implement. It's much less complex than you might think it is. So one of the things that made this so easy to actually infect other computers with was how small it was and how easy it was to load. Vitriol is less than 2,000 lines of code. It does very little. It's just that what it does is, pretty dangerous.
So I want to talk a bit about the level below the instructions. When you think about machine code and malware and stuff like that, most of the things you're thinking about are instruction level state. For instance, if you hook the SSDT, that's changing some instructions in memory and some tables and stuff like that. And this instruction set has a whole other computer implemented below it. Most people aren't aware of this because you don't work at this level, but if you're Intel or AMD or people like that, you're intimately concerned with this. Basically, every instruction you have is implemented as microcode. There's actually micro-ops and small instructions that are within the CPU. They're software updatable. Some BIOS updates contained signed microcode updates as well. And these microarchitectural details are then affected by the side effects and the various components that are used to implement these micro operations. For instance, things like the cache, instruction scheduling, branch prediction. All of these items are micro-architectural details that are influenced by the actual micro ops that are running within your CPU while it's executing instructions. And if you go below that layer, you even have a whole set of embedded hardware or external hardware peripherals that each have their own CPUs. A friend and I once tried to count how many CPUs you'd find in a typical desktop or laptop system. You got about 20 to 40, depending on the type of system, CPUs in there. You've got a CPU to run your display. You've got microcontrollers for your keyboard, mouse, power management. You've got basically your wireless chipset. Most of them commonly have like a MIPS or an ARM firmware on board. You have all these different complex computers within your computer, and you basically have like a chipset LAN within each computer. And you can use that against the hypervisor because the hypervisor isn't aware of the state of the peripherals unless it was intimately familiar with every peripheral and emulating it or potentially custom designed to trap a particular driver's access to that hardware. So what you end up with is an increasingly complex set of state which is contained within the chipset in the computer, which isn't visible at the instruction level, but you can observe side effects of that. And here in this loop of arrows, we show a typical VT operation where you're running a hypervisor and some instructions run, and you do something like RDTSC or CPU ID, which causes a VM exit. So that traps to sort of the VT component, VT microcode of your processor, which then decides whether or not, based on what trap flags are set, to jump to your VM handler. So we showed in this case it decided to virtualize it. You're trapping this particular operation. And that jumps back to instruction level execution. And it has some effects at the microarchitectural level. For instance, if you're virtualizing a read MSR, for instance, the read MSR instruction is actually not executed. Instead, the trap happens before the RD MSR is actually executed. And so it begins executing other instructions. And this is a nice low-level interface to the hardware, but it doesn't tell the hypervisor anything about what's going on below that level, at the chipset level, at bus level, hardware level, and other microarchitectural side effects that may occur because of this jump through the VM exit handler.
So let's talk really quickly about, with that detail in mind, and hopefully that helps you understand Vitriol a little bit better, how Vitriol actually works and what that actually looks like in the real world. What Vitriol does when it loads itself, Vitriol, our Intel VT rootkit, or Dino's Intel VT rootkit, what Vitriol does is it installs from a kernel module. So unlike Joanna, which we'll get to in a second, we didn't come up with a clever way to load it under Vista. From kernel mode, what it does is essentially it forks the processor, or it forks the machine into a guest machine and a host machine. And when we say fork, think of it like Unix fork. What you're essentially doing is you're taking the running context of the computer, the registers and the memory areas and things like that, and you're loading a separate guest operating system that shares exactly the same memory segments, the exact same state. So once loaded, the hypervisor and the guest operating system, and when we say guest, we now mean the hyperjacked version of OS X running. Once it's running, the hypervisor and OS X share the exact same memory. They're just code. They're regions of instructions that get called under different circumstances. Think of the hypervisor as a different kind of interrupt handler running on that computer, and then it's using VT to hide attempts to actually detect it. So one of the things that does is it allows Vitriol access to everything in the running operating system, which allows operating system level backdoors to run much simpler because it's essentially the same machine, the same memory, just running in two slightly different contexts. We introduced this idea of, you have user land in a conventional operating system which runs at a lower ring of privilege. So your user land is ring 3, right? And under that, you have the kernel, which runs in ring 0 with direct access to the hardware. And what virtualization, Intel virtualization and AMD virtualization does is it kind of sort of introduces a notion of a ring -1, which is where the hypervisor itself lives. And what happens is once it's installed and once the trap handlers are set up and once it's configured to intercept certain operations, certain instructions, like we said, instead of talking directly to the hardware, talk to our trap handler instead. And what you get is when you issue one of these instructions, like trying to read a model-specific register from the chipset, right? What happens is you get what's called a VM exit, which is the guest operating system, OS X, exiting from ring 0 and dropping down to the hypervisor to actually implement that instruction. And for the most part, what happens when you do that is the hypervisor itself issues the real instruction. right? So if you're trying to read an MSR from the chipset, for instance, the hypervisor itself would proxy that request directly through. It's going to allow most of those requests to go through unscathed. It's going to get the result. It's going to populate the state of the computer to emulate the effect of that instruction. And it's going to return control back to the guest operating system. That transaction is called a VM exit, which is exiting from the guest operating system, and a VM entrance, which is returning control back to the guest operating system. Now, like we said before, the hyperjacker gets to pick and choose which ones of these operations are actually going to be virtualized. So certain things, certain ways of talking to the hardware are not intercepted by the hyperjacker. For instance, certain interrupts and things like that will pass directly to the hardware, will not get trapped by a hyperjacker because it's not emulating everything. But certain other things will cause VM exits, and some of those things have to happen. Some of those VM exits and VM entrances are mandatory. So we've been talking so far about how Vitriol works and generally what Vitriol is, and I just want to contrast this with Joanna's Blue Pill. Some of you guys may be familiar with the challenge that we issued to Joanna. We didn't expect to get as much PR from that as we actually did, but Dino Daizovi and Joanna Rukowska released hypervisor malware, released hardware virtualized malware last year at Black Hat simultaneously. And their implementations, the underlying implementations are somewhat similar, but Joanna's is different in a couple of different ways, right? Joanna's hypervisor rootkit uses the AMD virtualization set, which is compatible enough with Intel's virtualization that Zen treats them almost like the same thing. Hers infects Vista and not OS X. Ours is an OS X rootkit. Hers is a Vista one. She has a clever way of loading her rootkit. We didn't come up with a way to compromise the OS X kernel. There are probably already plenty of other good ways to compromise the OS X kernel. We didn't come up with a new one. Hers implements network I/O. Dino's slide deck from last year has, as soon as we figure out how to do network I/O with Vitriol, we'll tell you how that works. Then we went to the conference and saw Joanna present hers, and it's like, why didn't we think of that? But Joanna uses the debug registers in the machine to intercept the network stack calls, to intercept frames coming to the machine. And using that, she's loaded an entire IP stack into her hypervisor, which is just damn cool, right? We haven't weaponized our rootkit to the extent that she's weaponized her rootkit. Ours is more of a proof of concept than hers is. And then she's done more things than we have with our rootkit to prevent people from detecting her. So for instance, you can virtualize the running machine, and ostensibly when you do that, you should be exposing all the operations of the underlying machine, including virtualization itself. That's nested virtual machines. So in a virtualized version of Vista, you should be able to run other virtualized guest operating systems under that. You can't do that with ours. If you issue VM instructions in ours, we trap out. Joanna actually apparently implements, as she said, she implements nested virtual machines. We don't know the extent to which she does or doesn't do that. What we're doing is we're giving her the benefit of the doubt. What we want to talk about are ways to detect hardware virtualized rootkits, even assuming that she's implemented everything that we can come up with that you could possibly implement to evade these types of attacks. But let's make it clear that she's done more than we have to make her rootkit harder to detect. And then her central claim from her talk was, this is the foundation. Blue Pill itself is not 100% undetectable, but it's the foundation of a path that takes us to 100% undetectable malware. And we're really interested in debunking that claim. We're not sure that anything is 100% undetectable, and we think it's a really interesting challenge to go back and forth between us and her to see whether or not this is true. And I think it's hard to prove whether or not your stuff is 100% undetectable if you don't have an adversary trying to detect you, and that's what we're trying to provide here.
So here's the central claim of our talk, which is that nothing is 100% undetectable. Every potential rootkit that's been out there we've found ways to detect it. So Peter's going to talk a little bit about detecting software virtualization.
So when people talked about virtualization previously, most people thought about the software-based virtualization. And no one seriously thinks those are undetectable anymore. We have, for example, in Virtual PC and VMware, emulated hardware, which is, in the case of VMware, the chipset is from the Bill Clinton president era, and it's really, really old now. We have the holes in virtualization itself that, as demonstrated by Red Pill, the SIDT instruction reveals that the system is virtualized. In the case of Virtual PC, we have a motherboard whose manufacturer is Microsoft, despite them claiming they're not in the hardware business. In the case of registry keys that, at least when the tools are installed in VMware, they will import registry keys from the host into the guest session. And while these are easy to remove, the strings that appear in the video and system BIOS are not quite so easy to remove, and there are many, many of those. There's also the guest-to-host communication channels. There's an explicit API for both VMware and virtual PC. In the case of VMware, a simple I/O port is accessed using particular registers. You can transfer memory and data back and forth. In the case of virtual PC, they use illegal instructions and illegal encodings of certain instructions, but in the same way that you can transfer memory to and from the host of the guest and vice versa. The timing variances are visible after a while as well, because you can query the read TSC, which is very, very difficult to trap for a software-based virtualization. And because the host can be queried for the real time using this API, you can see that the numbers diverge after the host has been running for a little while. So clearly, the software-based virtualization is very easy to detect, and we think the same thing for the hardware-based virtualization.
And we thought it was kind of important to point out the fact that software virtualization is straightforward to detect, because like all of you, we take our cues on how to secure things and what is possible and what is not possible from Slashdot comments. And our story got Slashdotted, and before this talk, we actually read through all the different +5 comments that were on Slashdot about whether it would be possible for us to detect Blue Pill. And a lot of them came down to things like, well, they're running VMware, and VMware is undetectable because it controls everything. And if you take away one thing from this slide, it's that if you're using something like a heavyweight virtual machine monitor, like a heavyweight hypervisor, like VMware provides, it's providing a complete containment environment that makes no attempt whatsoever to hide the fact that you're virtualized. If you are running malware containment environments that are trying to run things in simulation, it's more likely that you're going to see malware that takes advantage of virtualization by hiding itself when it detects that it's virtualized than it is that you are likely to see malware that's going to implement hardware virtualization. Do not assume that your malware cannot detect the fact that you're virtualized. Software virtualization is trivial to detect. Kind of the research project that we're working on right now started when we read Peter Ferrie's paper, which introduced one of the detection mechanisms that we're going to talk about later for hardware, but also just a huge variety of different ways to detect different hypervisors, such as parallels, which you can detect and crash with a single instruction, or VMware. So software virtualization is trivial to detect.
So we wanted to give you guys a mental model of how you think about different rootkits and the layers that they're implemented at. For instance, here's a typical kernel malware where, for instance, maybe it just infects one system call or just the SSDT in Windows. And it's a very small hook into the operating system. And it does its best to hide from other aspects of the operating system. And it has a wide variety of places where it can insert little bits here and there to try to hide itself. And it's difficult to detect kernel malware often because there's so many possibilities there. With x86 hardware, it tends to have a huge cross-section because there's so many different variants of it. There's so many different components to it, and it presents a really large cross-section. So keep this metric of cross-section in your mind as we're talking about this. We call it basically the amount of the original system that a rootkit must emulate to remain hidden. So the rootkit has two choices. It can either leave things unemulated and just pass them through, or it can try to emulate the entire behavior of that and trap all the behavior and try to avoid having any detectable difference between it and the actual hardware. Well, both of these result in a situation that's bad for the rootkit, because in the first case, if it tries to trap and if it fails to trap and emulate a feature, then we just use that feature to detect the rootkit. On the other hand, if it tries to trap and emulate a complex feature, let's say the cache behavior of 15 different models of Intel or AMD CPU, you end up with this ton of code there, and that code has a huge code base. It has a huge footprint, has a huge cross-section. And the side effects of that code and potential bugs in that code and things like that make it very easily detectable. So in either situation, if you take it to extreme, you end up in a situation where the rootkit author is at a disadvantage. And remember, the entire x86 hardware platform, it's a huge cross-section. There are so many different CPUs, as we talked about before, microarchitectural details, and all these are observable from a targeted detection algorithm.
So, I mean, if there's one point that we want to make in the whole talk for you guys to take away is you can measure almost any piece of malware by its cross-section. JavaScript malware has a cross-section. Kernel malware has a cross-section. Firmware malware that lives inside of the op-ROMs in your different peripherals has a cross-section. And if you want to evaluate malware by the size of its cross-section, by the likelihood that it's going to miss something or screw something up that you can detect, the entire x86 platform is a poor choice to actually attempt to insert yourself. It's much better to insert yourself in the kernel. You have a million different places that you can hide there. There are kind of nuclear options that you have to detect kernel malware, but they're not the most common options. Whereas if you're virtualizing yourself, you have one single fixed stationary target. Are you virtualized when you did not expect to be virtualized? And that's the cross-section that we want to exploit here.
A good example is the CPU ID instruction. It actually has a mandatory exit, meaning that you have to trap it, or it causes a trap whenever you have a hypervisor loaded. And in its normal behavior, CPU ID has a very specific small footprint. It only takes a few cycles. It doesn't touch memory, it doesn't touch the cache, doesn't touch anything else. It just basically stores a few values in the registers. And if you're virtualized, it has a huge impact because there are microarchitectural things that happen because you're jumping and running an entire VM exit handler. You're transferring control to things at the instruction level, which then have microarchitectural impact later on. And this is what makes it easy to detect.
You know, what I think is when it's actually, when we do questions towards the end, we can get you a mic and I can hear the question better. Also, we're introducing this concept of side channel attacks and things like that, which will introduce themselves many, many, many questions. Please evaluate our talk by whether we answer those questions before you have to ask the question. So I'm sorry if it's taking us a while to kind of get to the point on this, but we're getting to it right now, actually, which is we think that all the strategies that we're going to use or that people are going to use to inevitably detect hardware virtualized malware are going to fall into one of three strategies. The first strategy is side channel attacks. Now, for the past blah number of years, in the very next slide that we have, Nate's going to talk more about this for reasons that will become clear. We've been using timing analysis and resource consumption analysis of different systems to detect things about how the system is running. Namely, we can use timing variances, power consumption variances, things like that, to reverse individual key bits out of RSA implementations and AES implementations. If we could do that to break crypto algorithms, we're in a much better setting when we own the computer and ostensibly the hardware underneath it to detect virtualization. So that first strategy is side channel analysis, to detect places where virtualization perturbs the normal operation of the system. The second strategy is what we call vantage point attacks. And Nate just talked about it a second ago. We have a dilemma here, which is that in order to allow the system to be feasibly implemented, so we don't have to spend 16 man-years actually building it, in order to actually allow the system to be feasible, we don't implement all of the hardware that's supposed to run there. We allow certain requests to the hardware to pass directly through without being intercepted. Well, if you forget important ones, then the actual guest operating system, which is actively trying to detect you, can talk directly to the hardware. And in a variety of cases, the hardware will betray you if you're the malware author. So there are a whole bunch of places that you have to catch and make sure that you emulate, even though to get functionality working properly, you didn't have to emulate them. However, that's the other horn of this dilemma, which is this third strategy we have, which is the fact that as you try to implement those and emulate those different features, there are variances in how those features actually work. So if you don't get those perfectly right, you create differences that we can monitor for as well. So our talk talks about three different strategies of places that we're using to detect virtualized malware. And here's one.
We think that all those strategies will encapsulate pretty much every detection method someone can come up with. And in fact, we've gone through and implemented one example from each of these to show how it works. So in terms of side channel attacks, that's something that's actually not very familiar in the IT security world, even though it's become very relevant with remote network timing attacks being mounted against real systems like OpenSSL in Apache. So basically, a side channel attack is anytime you have a system where resources, instructions, cache, power, heat, sound, all of these side channels have been used to identify when data or logic-dependent processing has been done within a processor. So, for example, here's an easy one. This would be an interview question at my previous employer, where if you're looking at this, what's wrong with this code? Well, I mean, there's a lot of things wrong with it. For instance, it takes the size of the smallest string, but also this gives the attacker a side channel where if they time the amount of time it takes to return login failed while they guess various passwords, the string comp algorithm exits early. And so that will give you information about how close your guess is to the real guess, because each time you get a letter right, it'll take a little bit longer to tell you failed. And this type of attack was found early in '83 by Lamson on 10x. It's sort of the classical example of timing attacks. But it was mounted in a much more effective way against crypto later on when Kocher used, my former boss, used it for attacking RSA. He basically just used a stopwatch equivalent to time an entire RSA operation, and from that he was able to distinguish the number of squares and multiplies, and thus the key that was used. And he improved this attack later on to what's called DPA, or power analysis attacks, where you actually monitor the power consumption of a smart card, which is an embedded device. You can't see the keys directly, but you can see the power consumption of this, and it varies based on the key bits. But this varying is not always easily observable, so what you do is you collect a lot of traces and average them together, and then compare a given candidate guess against the mean. And from that, you can distinguish key bits, which when you ordinarily were looking at it, it looks like random noise on this oscilloscope. This was extended to what becomes relevant to, I think, our world here, which is remote timing attacks, where Brumley and Bonnet were able to mount an attack against a real RSA implementation, an optimized one using, it had Montgomery multiplication and Barrett reduction and all the rest in it. But they were still able, over a WAN connection, to extract the key bits of an OpenSSL process. And this is a really important breakthrough because a lot of people were a little dubious about this. You know, they say, oh, it matters in the embedded world, but doesn't matter in the IT world. Well, that was extended even more very recently with branch target buffer prediction timing attacks, where people could actually monitor the state of the branch prediction buffer and use that to tell if some other process running on the same CPU, for instance on another core or on the same core but subsequently, was affecting the branch target buffer, and thus they could tell what branches were taken in that code and what branches were not taken. And this is the one that's most relevant to us.
So, I mean, please, after this talk or whenever you guys get a chance, if you haven't read those last two papers, just plug everything but the dates, which I may have gotten wrong, into Google and pull down those papers. The Dan Bona paper, for instance, hugely important. First of all, it debunks the notion that timing attacks are difficult to pull off. But second of all, please think about the fact that what these guys did in their research project was they wrote code that pulled the RSA private keys out of remote computers using only timing differences over a wide area network connection. And we have a little bit more to say about that later on in the talk. And then the second talk is kind of the product of a long series of local timing attacks. These are attacks where you're using local chip features to attack machines. But it's relevant to virtualization as well. This is, again, the idea that if you have access to a machine that's doing crypto operations, if you're one user and there's another user doing something sensitive on the same machine, you can time microarchitectural differences, in this case, branch timing, which we'll talk about more in a little while, to extract keys from running processes. If you run an SSL server on a shared virtual host environment where other virtual hosts are running and may be under the control of an attacker, be aware that those attackers are in an extremely advantageous position to pull the keys out of your process because they have access to the trails that are being left in the microarchitecture of the things that that secure server is doing. So it's not happening yet, but you know, it's not an inconceivable attack that you could see general purpose tools to do that.
Right. And remember, we're here at the end, so we have local access to the machine. We're in an advantageous spot as the detector of this malware. So a common complaint is what real systems are too noisy. Hopefully, if you've read those other two papers, you'll find that real systems are not too noisy, but there are things you can do to adjust for that. So in this case, there's been a great paper that came out recently, only a few months ago, about how to optimize remote timing attacks. And you know, normally people think you have millisecond level jitter on a WAN connection. Well, Crosby and the rest here found that on a WAN they were able to compensate for the jitter by profiling their local computer and reducing it to about 15 to 100 microseconds resolution depending on the situation. And on a LAN connection they were able to get it down to 100 nanoseconds. Now remember, this is sub-ping time resolution in the processor, and it's an extremely important example of how using statistics you can reduce the noise that's affecting your measurements of the system.
And in crypto operations, that's really important because there's a noise floor when you're doing monitoring, right? That, you know, the fact that you can do over a LAN 100 nanosecond profiling over a remote system opens up a wide area of attacks. But on a normal local system, we have much better precision than even this. We don't even need the statistics to do that.
Right. So there's two strategies and things we can do about this. The first one is if there is noise and you can't get rid of it, then just take more samples and average. The more samples you have, noise is random. It's decorrelated from the actual operation you're doing. You're working, for instance, with secret key material that's constant, whereas the noise is random. Those two are different, and they'll separate into different piles when you average. And I'm simplifying the statistics a lot, but that's basically what happens. And because we have local access, we have higher resolution measurements than some of these remote timing attacks. But we also have another capability, which is we can briefly, very briefly, less than a couple instructions execution time, we can monopolize the CPU, run a few 100 instructions, measure some microarchitectural details, and then allow the CPU to continue. And when you're looking at AV scanners, they have a much bigger footprint on your processor than a couple simple probes like this. And you can repeat these periodically and correlate measurements. But the key thing here is that eliminating data-dependent side channels, all of them, in your software is very hard. Eliminating it in your microarchitecture is almost impossible. I mean, if you have two things executing on the same CPU, there are going to be dependencies between those that are visible in the microarchitectural details. And we'll talk about how to measure those in just a minute. First, we wanted to tell you how to find your own side channels. It's really easy, but sometimes requires a little bit of cleverness in figuring out what to do with it once you have found it. So the key is, first of all, look at all the resources that your opponent is using. You have to execute instructions in a hypervisor. You can't not execute instructions. You can't build a microcode level hypervisor using VT. You'd have to do it as a different kind of hypervisor. And so, for instance, you come up with one. Let's say they have to execute instructions. It has to somehow jump to a VM exit trap handler. Great. Now you've identified some of the resources it uses. Find out how you, from your vantage point, can measure those resources. Can you measure it directly? Is there a register you can read on the CPU that tells you, hey, there are 22 TLB entries in use from your ACID right now? No, there isn't that kind of thing. But you can actually modify and measure the side effects of the processor in the microarchitectural state by doing things like measuring the branch target buffer by just having a series of loops and jumping to various targets in those loops. And the CPU, because of the deep pipelining, has a branch prediction buffer. I mean, you guys have read Tom's Hardware, right? You see, caches, branch target buffer, things like that. This is what makes your CPU go fast. A misprediction is very expensive in modern processors. You have a deep pipeline, and if you predict the branch wrong, you have to refill that whole pipeline before you can continue executing instructions. So in this case, you can measure those by seeing, hey, is my branch taking a certain amount of time or less? If it takes too long, then you know something else ran, maybe an interrupt, maybe a VM exit, and it used some of the branch target buffer state because it made its own branches. It has to say if then at some point in its execution. After you've done that, you found a way to measure it, you know what kind of resources you're measuring, then what you want to do is take as many measurements as possible and eliminate the jitter using basic statistics. But the important point about all this is we've talked a little bit about crypto timing attacks. Those are much more difficult to mount against systems than a simple single-bit extraction, which is, am I virtualized or not? With RSA, 1024-bit keys, stuff like that, you have to do multiple measurements and correlate them significantly to be able to eliminate some of that jitter and to be able to be sure you have the key right. Because if you guess a key half right, guessing 512 bits of a 1024-bit key won't do you any good. But guessing a single bit is a lot easier, and it's a lot easier to measure this state.
So now we want to give you kind of an overview of the next class of attacks that we're using to detect virtualized systems. We want to talk about vantage point attacks, and I want to give you a fairly straightforward example. Last year when we presented Vitriol and when Joanna presented Blue Pill, there was a lot of conversation about the x86 timestamp counter, which is a counter that increments with the frequency of the CPU. And the interesting thing about the timestamp counter is that it's a source of time that you get directly from the hardware. And like we said before, you issue a CPU ID instruction, which is a mandatory VM exit on VTX hardware, right? Well, you can time the length of time that it took for CPU ID to exit. It should take 200 cycles. You can measure that directly. Call CPU, get the timestamp counter, call CPU ID, and reserialize and call RDTSC again, and take the delta and see, did CPU ID take an unexpectedly long amount of time to run? That's an obvious problem with hypervisor malware, but it's also pretty straightforward to defeat. It's pretty simple, right? The VTX hardware and presumably AMD as well gives you the ability to offset the TSC to present kind of a coherent notion of time to the guest operating system. So you can offset it when you run and mask the fact that the TSC, incremented much further than you expected it to run. So both Vitriol and Blue Pill take care of that attack. But there's a myriad of other time sources in your computer. Take the HPET, the high-performance event timers in the Intel chipset. There's an entire other alternate set of timers that you can talk to that Vitriol, at least, doesn't virtualize. It does not intercept attempts to read from the I/O mapped memory that the HPET resides in. You can read that memory and get a continually incrementing 64-bit timer that represents what time is going, how much time is elapsing on the computer. And if you don't intercept that, even though you've masked the TSC, you haven't masked the HPET. The two disagree with each other. First of all, the HPET tells you CPU ID is running longer than you expected it to. And second of all, the HPET is disagreeing with the timestamp counter. So if you forget to virtualize that, you have a smoking gun that you're virtualized when you weren't expected to be virtualized. Here's another one. The performance monitoring capabilities of modern Intel chipsets have performance counters for optimizing code and for compiler writers and systems engineers. And they count all sorts of different microarchitectural features. For instance, branch prediction misses. You can ask the hardware how many branch mispredictions there were directly. It's another counter that lives in I/O map memory that you can set up and then read from later. You can execute a span of code that includes VM exits because you've injected CPU ID or whatever into them, and then see if, when you execute CPU ID, that shouldn't actually change the number of mispredicted branches. It isn't a branch. It's talking directly to the hardware. But the branch prediction performance counters will betray the fact that happened, because when you actually entered the hypervisor, you executed all sorts of code, which did perturb those counters. So if you forget to virtualize that, you're screwed up. And finally, there are things like the AGP GART. The GART is an alternative memory mapping interface for scatter-gather I/O so that you can present to your graphics chipset the illusion of a contiguous space of memory that isn't actually there. It's an entire other memory translation capability in the system. You can program the AGP GART to point different pages of memory to different other pages of memory. If you don't virtualize the GART, you can use the GART to scan direct physical memory instead of whatever the virtualization, the hypervisor, tried to pass off to you as actual memory. Again, we presented that diagram before of you have the instructions, then you have the CPU, and then you have the chipset below it. And virtualization does nothing to the chipset itself. It doesn't actually protect the chipset. The chipset isn't virtualized. There's no idea that you're virtualized. That's a transaction that occurs between the instructions and the CPU. So if you miss things like these I/O things, like the GART, which changes in different versions of the software, like my MacBook doesn't have a conventional GART, then you can use those to profile as well and get the hardware to betray you.
One thing here that's really important is he's talked about neglecting to virtualize it, but there's the other side, which is you go and you try to trap every single one of these things. And these are complex pieces of hardware. For instance, I would challenge anyone here to run an arbitrary piece of code, run another arbitrary piece of code, and tell me how many branches should have been predicted or not predicted in that other piece of code.
And there's a variety of different things you guys can do to look at your hardware and look at your running operating system and find other vantage point attacks. Like we said before, there's a LAN inside of your computer that connects all these different peripherals you have on a bus. And each of those different peripherals has their own autonomous execution unit and its own autonomous DMA engine. And most of these peripherals rely on some notion of timing. Your NIC for retransmits, your wireless interface for beacons, your VGA. All these things have embedded time sources, but there's no one master time source that everything on the x86 platform uses. The timers are cheap. When you need a new timer, you put a new timer in. So all these different peripherals have their own local timing sources. Some of them are exposed directly to you. You can simply read them and use them to profile instructions that cause VM exits that shouldn't cause VM exits. But other timers are embedded and are not exported directly to you. But you can monitor behavior, like retransmits or like network I/O or all sorts of latencies in I/O and things like that, to infer the values of those counters and, again, time the instructions as they execute. Another one, model-specific MSRs. The MSRs on your chipset change from rev to rev of your machine. If you read from the wrong MSRs, you get model-specific interrupts or exceptions, right? You get like a GPF if you read from the wrong MSR. Not all of the MSRs are even documented. Talk to chipset vendors. They haven't written everything down. And then finally, all those peripherals themselves usually require access to the actual physical memory and themselves are not virtualized. You're not virtualizing the NIC, you're just virtualizing the instruction stream. So you can program other devices to make I/O requests from physical memory. They will see non-virtualized, actual, honest-to-God, non-masked physical memory. And you can use that to also scan physical memory and reconcile it to what you thought should have been there.
So one of the things we did when we were implementing this was, what's the process you can go through for finding your own bugs or errata, like crashing glass? So what we did was the same process that anyone here can do, which is you basically get all the data sheets and errata for a particular chipset or processor you're interested in. And the data sheets tell you how it should behave. The errata tells you how it actually behaves. And what you do is you look at the descriptions for each of these. For instance, if you go to the RDTSC instruction, there's actually a little pseudocode there. Well, when people implement processors, they actually write the microcode first. I know everyone's supposed to do design first, and most people do. They do most of the design. But then when it actually goes to implementing it, the implementation usually comes before the documentation. So what happens is someone goes and looks through the microcode and reads through it and says, okay, what are the orders of faults generated by this particular instruction? Okay, first it generates a GPF in this particular case. Then it generates undocumented instruction, undocumented opcode. Okay, so now you know the way the hardware behaves and the way it's supposed to behave. What kind of things there would be really hard to virtualize? What kind of things, if you exercise a particular errata in a particular chipset revision, is this something that if you had to virtualize it, you'd have to implement a full cycle-accurate simulation? If so, that's probably a good path to target first, because you're going to cause the hypervisor to have to be really complex if they try to respond to that particular
and that
behavior.
type of bug was actually the source of an actual security vulnerability a couple of years back, right? Where VMware and an actual running instance of VMware changed the order in which exceptions were delivered to the guest operating system. And the guest operating system, which was a version of Windows, had a dependency set up between the order in which those interrupts or those exceptions were delivered. And if they were executed in the wrong order, a data structure or a pointer wasn't initialized properly. And the net result was that userland code could crash the running version of Microsoft Windows 2000 or whatever it was, right? So VMware actually introduced a crashing security vulnerability into a version of Windows by delivering interrupts in the wrong order. You have to actually target that. You have to actually try and find it and execute it and make it happen, because it doesn't happen normally, right? Functional correctness is different from correctness with an adversary present. So if you go look for these things, you'll find places where hypervisor authors will mess up the order in which things are supposed to be delivered or the way that behavior is supposed to work.
And especially, there's a lot of times people think errata just means, oh, it'll all be fixed in the next version. There are a lot of these that are marked won't fix. I mean, the equivalent of this is always going to be the same way because it's too complicated to fix or introduces too many other bugs if you fix that behavior. In fact, if the operating system depends on that behavior, sometimes you can't change the microarchitectural behavior. So we want to talk about our implementation of a framework as well as some individual tests.
And I'm going to blow through this pretty quickly because Nate is going to bury you in technical detail in just a moment. But we've basically implemented a couple of things. We are releasing code for this. So, we're talking about a lot of the general purpose stuff because the talk would take too long if we got into too much detail. But we're releasing code for this. You guys will actually be able to see how this stuff works and how to probe for virtualization. And we'll get into more about how you'll test that. It's a fairly interesting answer that we have for that as well. So, but we're going to provide with you example implementations of 3 different detection scenarios. We actually think that these detection scenarios will detect Blue Pill as it exists today. We issued the challenge. Joanna didn't accept the challenge because, to be honest, our challenge probably wasn't fair, short notice, and all that other stuff. But we believe that right now that this stuff would actually work against her. But there's a myriad of other things that we can implement within the same framework to extend that. Our argument is not that it's impossible to write malware that I can't detect with my current code. Our argument is that it's impossible to write malware that is more undetectable than malware has been to date. It's still a cat and mouse game. So Nate's going to talk a little bit about one of the first of those detection techniques, which we'll show you code for.
Okay. So quickly wanted to introduce a microarchitectural feature. Maybe some people here are familiar with it. I mentioned Tom's Hardware before. How many people have heard of TLB before? Great. Excellent. A lot of people. So TLB, just to be quick, is a cache. But it's a cache for your page translations. And it works just like the caches for instructions and data. Basically, you have a 3-level page table here. It's 4-level if you have PAE enabled. We're showing the simpler version. And the virtual address is shown on the top right. And the virtual address is broken into various portions. And those portions are used to decode or traverse this 3-level page table here. At the bottom, you have your page table entries, which say, at this ultimate physical address, here's the virtual address, here's the physical address that it maps to. And this cache is not directly visible from software. You can't really ask the CPU, hey, which entries in my page table are actually cached in the TLB and which ones aren't. But what you can do is you can affect it through side effects. So for instance, if in a traditional operating system, if you move CR3, if you store to it, or CR4, you can cause a complete flush of the PTEs, where the TLB goes and rereads all the PTEs from the current executing OS as you touch those page tables. You can also basically flush individual pages to optimize this. So people are focused on performance of optimizing task switches and eventually optimizing VM switches. And that's how this behavior gets introduced. But you can as I said before, you can indirectly affect the TLB when you read, write, or execute from a page. There's two TLBs, instruction and data, just like there are two different caches, instruction and data caches, and it's associative like other caches. The key thing here, though, is that when a VM exit occurs, either mandatory like CPU ID or optional, if the VM author goes and starts trying to trap individual I/O operations to various ports to try to emulate various hardware things that we're checking for, then they're introducing various ways that a VM exit will occur, and then that leaves a trail in your TLB, it leaves a trail in your branch target buffer, it leaves a trail in your caches even, that we detect through side effects. General sequence of our tests that we've implemented, and this applies to most of the side channel attacks. You can take this basic pseudocode and write your own side channel detection. So basically what we do in this case, though, is we desynchronize the TLB, and we color memory by accessing it in a particular way that is intended to affect the TLB on all existing and future processors. Execute a test instruction, or a probe, as we call it. One is a simple no-op, which obviously should do nothing on all systems, including those that are virtualized. And we also execute CPU ID, which should do nothing on non-virtualized instances and should do something very drastic on virtualized instances. Then finally, we read memory to observe the side effects in the TLB. We tried to represent this graphically, and go ahead and take some time to look at this. Basically, there's several different phases of this, and the first phase is where everything's synchronized. And this is what your OS tries to maintain the system in for performance reasons. You want the TLB to match as closely as possible to the PTEs that you're actually using. Otherwise, every memory access gets slowed down. That's the whole reason the TLB exists. So in this case, your operating system does things, and even your hypervisor does things to try to optimize the mappings and make sure that they're all coherent. Well, what we do is we take that initial state, and we intentionally desynchronize it. So what we do is we write to some page table entries without notifying the processor that, hey, we've changed some things, you need to reload your cache. And that's what we're supposed to do, but in this case, we're not doing it for a particular reason, which is once it's desynchronized, at this point, we can detect the side effects of the size of the TLB, and we can also do timing using this. So basically, in two cases, let's assume we are virtualized. The first case, 3A, shows where we are virtualized and the CPU ID, for instance, caused a VM exit in the VT system. Well, in this case, basically, there's an entire TLB flush. So when we come back and we start running again, we'll find that the TLB has basically been emptied for us. Well, CPU ID is not supposed to do that. It doesn't touch memory. It only touches registers, and it doesn't do any branching, definitely.
That's not a timing difference, right? That's a functional difference, right? By desynchronizing the TLB, we gain the ability to essentially set it up so the same address in two different contexts points to two different pieces of memory, depending on how you're actually accessing that memory. So we set that condition up. We desynchronize the system like that, and then we come back after we issue a CPU ID, and we see if the system is in the exact same state. It's a single instruction. Shouldn't change that much on the system. We've quiesced the entire system. We've brought all the different processors on the system in line with IPIs. They're all, not running at all. We've, for microseconds, halted the whole system, set this condition up, issue a CPU ID, and then afterwards what we see is, after we issue the CPU ID, we read different memory out of those same addresses. It's pretty obvious to see that you're all of a sudden, instead of reading the 0xAA that you expected to read, now you're reading 0xBB instead.
So if you see in the bottom case, AMD has introduced an optimization here where they use something called ACID, which makes it so the entire TLB doesn't get flushed, but there's still things which do get flushed, and it's unintentional side effects. But you can see here the three green pages at the bottom are some pages that have unintentionally leaked from a hypervisor. There's a little dispute about this, that, hey, ACID's magic, it's going to fix everything, we can make TLB entries never get flushed. And that's not actually true. ASID is application space ID. It's kind of a new feature in AMD processors, which tries to prevent unnecessary flushes of the TLB, for instance, during VM entries and exits, by tagging individual TLB entries. So now the processor knows at a microarchitectural level which VM instance created these TLBs originally. And it can, but the key thing about this is it was designed for performance optimization. It's slow every time you flush the TLB, so let's try to avoid that. But it wasn't designed for transparency. If it was designed for transparency, it would 100% lock every single entry in the TLB when a VM exit condition occurs and reload 100% of it when it comes back. But in actuality, because the processor can't predict what instructions you're going to be executing. It can't predict eviction of at least a couple entries. And there's two cases that are mandatory when you're implementing a VM. One's that you have to read the status that caused you to exit to figure out what you're going to virtualize. So there's one page that leaks there. And second of all, you need to run at least one instruction in your hypervisor. Otherwise, it's not very much of a hypervisor at all. And when that instruction executes, you now evicted one instruction TLB entry. And if you have a really small hypervisor and you pack it into 4K of memory, you could use a 2 meg super page, for instance, you could avoid actually evicting too many. But there's still a small side effect that's directly observable in the size of the TLB after we've run our test.
And again, the perception is that, because of, my slide's coming up next, I might as well stand.
Okay.
The perception is that you're only leaking 1 or 2 TLB entries there, so it's going to be hard with any precision to time those out. But again, I want to repeat the fact that this is a functional difference. We had memory that was marked all AAA before. We issued CPU ID. You leaked the TLB entry. I don't notice the timing difference because of that. What I notice is that I'm reading through a string of memory that's all supposed to be AAA. All of a sudden, I get a BBBB there for some reason, right? That's a leaked page in there. So it's a dead giveaway when you actually execute, unless you can find a way to make sure that none of your TLB stuff leaks. It's obvious that you've actually flushed TLBs. And again, that never happens on normal individual instructions running in ring 0 with no preemption enabled.
So this is a quick description of the pseudocode that we actually implemented. He talks about how you fill a page with A, you point the PTEs at it without flushing the TLB, you look for B. Once you found it, you've sized your TLB. You found there were 20 entries in it before we ran. The key thing here is there's some people who have talked about this also, and Peter introduced it in his paper. One key optimization we had to do is you need to walk backwards through your PTE cache, because as you walk forwards, you're actually flushing entries as well. So you need to simulate the LRU algorithm that's being used by repeating it in reverse order. So our test actually does that. We also sized the instruction TLB. It's just like he said before, reading A or B from a given page, except in this case, we actually call each page. And we're jumping to pages in memory that we filled with a special instruction pattern. If we see a 1 when we return, it's the old entry. If we see a 2 when we return, it's the new entry. It's very simple. And it follows the same framework as the other one. In fact, it's the same test, actually, with just a different flag passed to it. There's a couple key things which we haven't yet implemented that would be based on the same design pattern. One is branch target buffer. And we talked about that before with timing attacks, where you can actually, by just running on one thread, a series of jumps. So I'm going to jump to target A or target B, and examine how the branch prediction affects that when the timing difference is how long the jump takes. And this allows you to do the same kind of test where you can basically run your test instruction, your probe instruction, and then vary the timing there. And also cache invalidation, which we really could do a whole talk about this, but this is a direct functional difference as well, where there's an INVD instruction which can basically throw things away that are in the cache. So you can point at a specific cache entry and say, don't write this to memory, discard it immediately. And what you do is you do the same thing we were talking about before. You walk through memory, filling the cache pages with a given pattern, and then what you do is you INVD those things after running your probe instruction. If some of those things actually hit memory and you see a BBB in memory, then something else ran in between and accidentally caused the cache to be invalidated, or they replaced a few things in the cache. And so those things got written from the cache to main memory. And just by reading a pattern from memory, you can tell it's something else ran. And this is very difficult. There's no ASID for cache. There's no such thing as that. So INVD gives you a really powerful way of sizing your cache. And nothing can execute without being loaded into the cache. Nothing can avoid that. People can do weird things with like setting bits on pages to uncacheable and stuff like that, which introduces a timing difference. So we basically have this fork where someone either has to introduce functional differences or try to simulate everything and introduce a timing difference.
And as an aside, because I can go through the HPET thing really, really fast, because it's exactly what you'd expect it to be in terms of a check, right? I think one of the conventional answers to how you would defeat, for instance, the functional problem of you can invalidate cache entries without writing back their contents to actual RAM. One of the answers to that seems to be that you could detect the detector. And when that happens, you can unload the hypervisor for a little while, right? Persist yourself into the kernel somehow, and then reload yourself back into the system, right? As an answer. If you take your hypervisor and you load it into the kernel, I will have a harder time detecting you. My suggestion is stay in the kernel, because I'll have a harder time detecting you if you just stay there than when you go back in and miss another one of my detection attempts. I think we all have probably the same opinion about how good code is at monitoring what other code is supposed to be doing. And we believe if you reduce the problem to the point where her detection code has to go and see the fact that we're trying to detect it and somehow infer the intent of that code, she's in a bad spot to begin with. But we agree that kernel malware is harder to detect. If you submarine yourself into the kernel, you're doing a better job of hiding from hypervisor detection. And if you want to hide from hypervisor detection, stay in the kernel. The HPAT example is really simple, right? We can just give ourselves an alternate timer besides the masked TSC, which we've done. We did this in OS 10 right now, where OS 10 is great. You can wire physical memory directly into user land processes. I have a shell script right now that has access to the HPAT. So we can use that as an alternate timing source to just directly verify the fact that that code took longer to execute. Like we said before, there's a variety of different timers in your machine. The one everyone thinks of immediately is the 16-bit programmable interrupt timer. You also have the battery-backed RTC. Then you have funky timers like the LAPIC timer, right, which is much faster than the RTC and much higher precision. Has to be virtualized specifically. You have to go in and make sure that attempts to manipulate or access the LAPIC timer are directly caught. You have this problem where CPU frequencies vary. And like we said before, timers are cheap. We have this problem where we need a consistent timer even though the CPU is running at different frequencies. It has to be a high precision timer. We'll enter the ACP timer where the ACP system itself provides a 24-bit timer that's 3 times as fast as the PIT. If you don't virtualize the ACP timer, which is present everywhere, I can read the ACP timer and time the fact that your code is running. Then you have the implicit timers. Take VGA blanking, for instance, right? Your VGA refresh is itself a clock. It's a readable clock. There's a register that you can read to see whether it's running. You can pull it. You can time the VGA interface on, module all the mode setting and stuff you have to do that, and get yourself another clock that you can use against the virtualization system.
Okay, we're going to skip the errata checks.
Yeah, one additional thing we did was we're up against nested hypervisor implementations, so we wrote a VMCS state fuzzer that goes and tries to probe all the different checks that the VT documentation talks about to make sure that you're delivering the right exceptions in the right order. So we can fuzz the VMCS structures and make sure that when you claim to load a new virtual machine, that you're doing it precisely like an actual implementation of SVM or VTX would do.
Skipping to the end, there's a lot of things that our framework can support in the future and that we plan to implement. Here's some of them. But our main point of this is that none of this is really important anyways because there are exactly 3, I think, VT-type rootkits we've counted, and none of them are in the wild infecting systems. So we're kind of tired of wasting our time talking about it. So we'll put the bat signal out, and if it ever becomes a problem, call us, and we'll reactivate the code.
One additional piece of code that we're releasing, binary only right now, is the simulator environment for this, or the hardware virtualization testbed. We realized when we talked about releasing the code, you guys don't have much to detect because we're pretty closed-lipped about Vitriol. Joanna justifiably closed-lipped about Blue Pill. So you don't have a hardware virtualized rootkit to test. So we'll provide you with a test bench environment that you can actually run this against. Only works on OS 10, only works on 10.4, doesn't have a backdoor installed in it, loudly advertises its presence, likely to crash your machine, only works if you boot the system up into CPUs equals 1 mode, which is, every single common VT implementation in the world is a multi-core implementation. So not at all useful to an attacker. You'd have a much better time reading the Zen source code if you wanted to learn how to write hardware virtualized rootkits. But we'll provide a test environment as well for it.
Okay. And in conclusion, where this is going to end up ultimately is people will give up the idea of 100% undetectable. They'll give up the idea of a generalized solution being the silver bullet that kills all rootkits or makes a rootkit completely undetectable. And what will end up is what looks like the standard AV ecosystem, which is people research the last code that their opponent released. They write things to specifically avoid or patch that particular code to make it ineffective. They deploy it. The cycle repeats. The other opponent gets a chance to do this. And this cycle is common in all systems. It's really boring, but you'll see everything devolve to this at some point. So thank you for your time.